All right, everyone. Here I have something kind of simple. I have this is a solenoid, which is basically just a coil of wire. So wire goes in one end, and well, the connection's there. Then it loops around a million times or hundreds of times, and then comes out there. So it's just basically a coil. But this goes by many different names. This is a versatile piece of equipment. It's sometimes called a solenoid, sometimes called an electromagnet. If we run current through this, then this will become like a north-south magnet. So electromagnet, also called an inductor. And these are used in making oscillating voltages. So the source of radio waves, microwaves, are like a capacitor and an inductor in a circuit. So it makes oscillating things, or these types of devices. Also, it's called a choke, and they are used for actually mechanical uses like power locking of your car doors and stuff like that. So a lot of different uses. Here I'm gonna show you a kind of a remarkable thing, because all I have is this coil of wire plugged into my galvanometer here, which this is just measuring microamps. So it just measures current flowing through it. So there's no battery here, no source of electric potential that we know of, and there's no current. So then here's the magic part. I bring a magnet here. So I just have this bar magnet, and well, if I put it near the coil, I don't see any current. It's not really anything happening there. But if I bring it inside the coil, well, there's a very small thing. If I move it slowly, you don't really see much. But if I start moving faster, maybe you saw that, I'll pull it out pretty quick. 3, 2, 1, go. So notice I got a little current. When I go into the coil, I get a little current. When I come out, I get a little current. So it's a change. There's actually magnetic field that's going in these loops. And it turns out when the magnetic flux going through the loops is increasing or decreasing, when it's changing in some way, then I get a current. So for example, if I put the magnet just in there, it's not like the magnet is like magically making this current. If it's there constantly, then I don't get any current. But let's say I let it fall out, for example, that'll go pretty fast. Let's see how the current does here. Oops, that was shiny. Try that again. I think there was a glare. I'll just drop it through here. Oops. It's gonna be hard to do this. All right, try this. So there you go. There's like a little burst. So you're getting a little burst of current when you're changing. And notice it's like one way or the other. If I go, this is the north side. So if I go north in first, let's see, not much. Let me try that again. Okay, so I'm getting a positive reading. So the current's going around one way when I put the north in first. When I pull the north out, it goes the other way. And then I'll switch it around. Let's say I switch with the south. You can probably bet everything's going to reverse. I go in the south first. I got a negative current, or I guess a leftwise current here. And then I pull the south out, and then I get a rightwise current. So it's like always reversing, and we'll look into that. But this is what this whole chapter is about. This crazy thing where a changing magnetic flux creates, actually there's a little EMF, like a little battery is generated around the loop. So it's actually a different kind of electric field that we haven't seen before. All right. All right, so that's my little beginning demo. And now I want to jump into just go straight through the material here. So please be ready to answer this question when we come into class Tuesday. November 2nd. All right, so what is this? The chapter opening question. So good to take a look at. In the photograph above, the bar magnet is inserted into the coil of wire and is left there for 1 minute. Then it is pulled out from the coil. What would an observer watching the galvanometer see? So you can pause this, take a look at those. We've pretty much gone over that already. All right, so this all this stuff comes down to a changing magnetic flux causes, and what I'll call an induced EMF, basically like a temporary battery. There's like an imaginary temporary battery. It's kind of weird. It actually encompasses different phenomena. So flux, if you'll remember, we defined electric flux as phi sub E was like the electric field times an area, and then the cosine of theta. And so magnetic flux, we're going to define in the exact same way, phi sub B, and that's the magnetic field, the area cosine theta. And so just to remind you of flux, what is flux? You can think of it as like the amount of field piercing an area. So for example, let's say I have a uniform magnetic field, just as a nice simple experiment or just simple definition. If I have this uniform magnetic field, and in here I put like a piece of area, like a little area like this, we could look at from the side, just kind of like this, just a thin area. So we can just see it angle on. You've got some area. Basically, the idea is how much of this field is like just going through there. And so you've got like an effective size for it. If I look at the normal, I want to think about this cosine, because to me, it's like, what is that? Why do we have a cosine here? What is that? So I'm going to look at this. This is what we call the normal direction, perpendicular. And your book doesn't actually use that word, but in math, we just use normal to mean perpendicular to a surface. Right? And so if we think about the magnetic field here, it's got these different components. I have this, if we imagine at this place, there's that little area. We're looking sideways on the area. Here's our magnetic field vector. It's just a finite length vector. But look at this. Some of that magnetic field goes along the normal vector, and some of it is perpendicular. And so we can think of the magnetic field as like one component that's perpendicular to the surface and one component that's along the surface. We have the B along the surface, and then we have the B that's perpendicular to the surface. And you can, if you think about vector addition, we've got one plus the other here. So I've got B perpendicular to the surface. And that's the component of B that determines the flow. If you can imagine this was like water flowing through a hoop, and the area is like the hoop. Well, if this hoop is slanted like that, you got less effective area, and so you got less flow through that hoop. And so the angle, I should have mentioned, is this angle there. So if this theta is the angle between the magnetic field and the direction perpendicular to the area. Okay, so what about the magnetic flux? I'm just going to go right out and say Faraday's law. Your book kind of, well, your book is somewhat direct about this. Some books kind of hide it more because it's just a little, it's just a big statement. So Faraday's law says that the induced EMF is equal to the rate of change of the magnetic flux. And then there's this minus sign, which we'll talk about. That I wouldn't worry too much about that minus sign. We're mostly going to deal with it straight on, so you won't have to really remember that too much. But that's actually called, this is such a confusing minus sign. It's got its own name. It's called Lenz's law. And I'll mention that a little bit later. But I just want to get the general idea across. If your magnetic flux is changing in time, then you get an induced EMF. That's why the needle was only changing when I moved the magnet. It doesn't matter what the magnetic flux is, just as long as it's changing. So we could put that in English. The English version would be, well, I think the English version we already have up here. That's the general thing. The changing magnetic flux causes an induced EMF. And furthermore, this equation is really equals. It's like you can do the units and you say, how fast is the magnetic flux changing? For example, let's just say real quick, I have a loop. Let's say this is a wire. I have a little wire loop. And let's say it's 10 centimeters on an end. So it's L by L, like a square, just for simplicity. So 10 centimeters equals L. What's the area of this loop? I would think 0.1 meters times 0.1 meters, L squared is 10 to the minus 2 meters, 0.01, well, square meters. So 1/100th of a square meter. So that's the area. And so let's say I had Earth's magnetic field here, just a regular old compass field, B Earth. And I think that's like micro Tesla. So let's just say the magnitude of that is 100 micro Tesla. So, so let's say I had a changing flux. How could I change the flux? Well, you can move the magnet, but in this case, it's the Earth. So you can't really move the Earth. What you can do is actually change the loop. Let's say, this is say the initial. So B is going, say again, B is going like this, and say I have my initial state, and then I quickly rotate it. So I rotate down, and so then we've got a final state. So I rotated. So what did I do? I changed all the magnetic flux, because the initial magnetic flux was my B times the area. And in this case, theta is 0, just for simplicity. And so then we can do 100 microtesla, 10 to the minus 4 Tesla times 0.01 meters squared. So that's 10 to the minus 6. And here's the units of flux, Tesla meters squared. So that's our change in flux. That's my initial flux. But the thing is, the final flux is 0, because after I rotated it, it's done. So if I want to calculate my total change in flux, then I do a phi final minus a phi initial. My phi final is 0. And let's just do the absolute value. We'll mess around with the magnitude later. but really it's just whatever we started with, that's our total change in flux. Then the delta T, I didn't say what that was. So just imagine how fast could you do that? Maybe 1/10 of a second. So we'll just suggest, what if I did this, about as fast as I could, 1/10 of a second, maybe 1/20th of a second. Then we can compute our induced EMF. The magnitude, delta phi, B, delta T. And so we've got 10 to the minus 6 Tesla meters squared divided by 0.1 seconds. So that's my situation, and looks like we're going to get a 10 to the minus 5 Tesla meters squared per second. And so let's look at these units, Tesla meters squared per second. In principle, this thing says those should be units of volts. So are these volts? Well, one thing I like to use the force law, QVB, to think about the units of a Tesla. So we just try that. So a Tesla is the units of, well, the units of B is a Tesla, and that's the units of force over QV. So I'm just going to plug those in. What's force? Newtons. What's Q? Coulombs. What's V? Meters per second. So that's my Tesla there. Then times meters per second. And so I'm canceling those meters. These seconds look like they're canceling. And then I've got a Newton times a meter over a Coulomb. And so a Newton times a meter, that's a joule. If we think force times distance is work, I've got a joule per Coulomb, and that is indeed volts. Energy per unit charge. So I do have 10 to the minus 5 volts. That's pretty small volts. I don't think you can measure that with with the voltmeters we have. You might be able to do that, 10 microvolts, but it would just be for an instant. Just, while this is changing. Once this is done changing, then it will stop. So it only goes for 0.1 seconds. So, but you essentially would have a little, I think I add some too many arrows here, a wrong way arrow. If I want to think about current, yeah, we'll think about what direction is the current next. But if you want to think about that, you will have current while this is happening. There would be a little bit of current. We could actually figure out how many amps that would be. Pretty small, but the resistance is small, less than an ohm. So you're getting, it would be significantly less than an ohm if it's just a wire. So then you'll get 10 to the minus 4, 10 to the minus 3 amps. You could potentially get a milliamp for just 0.1 seconds. So that's the idea. All right, the next thing I want to talk about is actually predicting which way will the current flow. So this is induced current. And so the answer, if that's the question, the answer is something called Lenz's law. And it has it's a very peculiar statement. So it's not that bad once you get used to it. The idea is this: a current produced by an induced EMF moves in a direction so that the magnetic field, field created by that current. So the induced current is creating a magnetic field. That's the first thing to recognize. And Lenz's law has to do with that magnetic field created by the induced current. So there's a B here. And so the idea is, one thing to remember is this B is an external magnetic field. So that means something else, not from this loop, something else actually created this B, and this loop just is near that B, some external B. But Lenz's law is actually talking about the current produced by an induced EMF moves in a direction so that the magnetic field created by that current, and I need to finish the sentence, opposes the original change in flux. And that opposes, that's the minus sign where it says opposes. There's a minus sign in Faraday's law. And so that's the opposes word. And so let's work off some examples of how this goes here. So let's say I have a coil like this. I'll do a couple of different situations. And so let's say I have a bar magnet, north, south. And first off, let's just say, what if the velocity is 0? If it's sitting there, then there's magnetic flux. There's still flux, lots of flux going through this loop, but the current is 0 because there's no change. You got to have change. And so what happens when they have a magnet that's actually moving? So let's start moving this magnet towards the loop. So what happens when it's moving towards the loop? Well, my magnetic flux is actually going through the loop upwards. And now here's the thing, it's increasing. And so the idea is this opposes. So there's going to be an induced current. And so which way does the induced current flow? The idea is the induced current is going to flow in a direction so that the magnetic field created by that current opposes the original change in flux. So here we have a B that's increasing. It's getting bigger. The flux is getting bigger. So the induced current wants to make a magnetic field that's actually, instead of pointing up here, is going to point down to oppose the change. And so here's Lenz's law. Lenz's law is going to tell us this, that B induced must be down there to oppose the change. And so then the question is, which direction is going to give you that? And I guess I probably should do this, my physical self. Okay, so I just want to go over just a little bit about these current carrying wires again, so you can remember this stuff. If I have a current carrying wire, carrying current like that, if I want to know the direction of the magnetic field, I grab it, and with my thumb in the direction of the current, and I know, well, field goes in there and out there. So that's first piece of information. Then the second piece of information is, what if current's going around in a circle? So, well, a circle is kind of like a line, if you zoom in or zoom out. So like, if I can do this here, I can also do that there. And so if I grab here, that's telling me my magnetic field's in. And actually, if I go all the way around, I get the same answer. So it's in like that everywhere. And so it's just in there, it's just in. And so that's how you can think about the magnetic fields from a current loop. So in the case we were just talking about, you've got a magnetic field going like this, it's increasing. And so we've got a wire loop that's like this. Well, let me try that again. Like this. And so the induced field has to be down like that. And so which way is going to create a downward field? I imagine grabbing onto this wire, and I want the field to go down. So that tells me my current's got to go this way. So current's going to flow that way into the page there. Notice if I stick my thumb into the page, I get down, and I go around, I get down everywhere. It's going to come out of the page here. So that's how you can tell. If my field's increasing upward, then I must have a field looping around like that. And so that's in the case where my north, or maybe you guys can't see all that north-south, velocity moving up. So let's do the next one. Why not? So if I'm here then, let's say, here's where it gets a little weird. Let's say, this is meant to say north. Let's say it's actually moving down. So here's where it's, this is induced, I should say. That's your induced field. Well, what happens if it's going down? We know it's going to go the other way because that's hopefully what you saw in the original little demo. And so now we've got B. B is still pointing up like this, but it's actually decreasing. So this is a big difference. We're decreasing here. And so what does that mean? That means that the induced field wants to oppose the change, but these vectors are getting smaller and smaller, so the change is down that way. So in this case, we want our induced field to actually point up, because basically the way you anthropomorphize it is like the loop doesn't want the flux to change. If the flux starts changing, then the loop does what it needs to do to keep the flux to stay the same. Although it can't really keep it the same, it can only do a little bit. So as this is moving away, the field gets smaller, and then of course it's going to go the other way. So then you're going into the page there and out of the page here. And again, one other way to think about it with loops is, so I like to think of a loop as like, think about it the same way I would like a long straight wire for the field. But once you get the hang of it, there's another right-hand rule you can do. So I know here that if the current's going around like this, field's down in the middle, you could also kind of do this. So basically, if the current is going around like this, then the field in the middle is that way. It's like that. And if the current's going the other way, so here, if the current's going, I guess, to you guys, it's counterclockwise here. If I shift this, actually, I'm not sure how the video flips around, but yeah, you can use this anytime there's a loop. So if I want the field to be up in the middle, I can use my thumb and say, oh, the current's going to go around that sense. Here, I want the field to be down. So I go around like that, and then I know the current goes around like that. So it's another similar right-hand rule. All right. And you have a similar behavior if you actually put the south end first. And so changing the magnetic field is one way. And actually, this is the most interesting in the sense, for, if you think about the what's actually happening, because nothing is moving. No charges are moving in a magnetic field here. So it's not those. It's not this force that's doing this, F equals QV, QVB sine theta. That's like not what's happening, because there's no V. And there's no velocity here. No charge inside that wire is moving. So it actually turns out there's something more fundamental happening. An electric field is created here. Although there are different ways to get changes in flux. So not all of them involve an induced electric field. That's actually the craziest thing we're going to talk about in this section. Let's see here. One example is not here. All right. So here's something that I thought was kind of cool from the textbook. Induction heating. I don't know if anybody's ever seen one of these, but an induction stove, in an induction stove, an AC current exists in a coil that is the burner, a burner that never gets hot. Why will it heat a metal pan, usually iron, but not a glass container? So this pad here, notice the pan's touching, it's not hot. What's going on? It's got a current an AC current. So I'll answer the question for you guys. An AC current, that's a changing, well, it's going to create a changing magnetic field, and that's actually going to change the flux in the metal. So this metal here, you don't necessarily have to have a wire or loop. For us, it was very simple. Actually, I should put the direction of the current here. For us, it was very simple to think about a little current going around in the loop. But you still get these same effects, even if it's not a wire loop, even if it's a piece of metal. So change in flux inside metal creates something called eddy currents. You've just got these kind of complex currents swooping around inside the metals. And this is actually used in metal detectors. That's how they function. You're generating eddy currents in a piece of metal, and then the eddy currents themselves create magnetic fields, and those can be detected. And so why will it heat a metal pan? Usually iron, because of currents. It's actually the power. If you guys remember I squared R, you have currents in a piece of metal, the metal heats up. And so, but not in a glass container. Well, you can't really generate, there's no free electrons in glass. So then you don't get those currents. All right, here. And let's test our stuff about Lenz's law. Conceptual example 21.3. There it is. Okay, so practice with Lenz's law. In which direction is the current induced in the circular loop for each of the situations? So try these out. Think about these and make sure you come to class ready to discuss these. So study these. Maybe I'll do one of them for you. Let's try the first one. Pulling a round loop to the right out of a magnetic field which points out of the page. And so what are we supposed to do? In which direction is the current? In which direction is the current induced in the circular loop? It's a weird comma. I think that comma is an error. All right, so which direction is the flux changing? Basically, think about this. As you're pulling it out, it's going from having flux coming out of the page to flux 0. So it's losing that flux. So the idea is the loop in here, I'm going to anthropomorphize the loop. I'm going to say the loop wants to keep the flux constant. So that means it wants to have a B induced points out of the page. So that's the idea. Our B induced has to point out. And so which way is going to give us that direction of the magnetic field? Here I will use the new right-hand rule thing I kind of told you about. If my thumb is coming out of the page, then the current is going around that way. So then that's how I would use. The other way would be to consider the loop to be a long straight wire and grab the loop at some point, and you want your finger to come out of the page. You want your fingers to come out of the page, so then you're grabbing it. The other way is like you're grabbing it with your fingers coming out of the page, your right hand like that. So that gives you the same answer. So it's both. It's either your thumb or your fingers telling you the direction of the current. So try those other ones. And notice these don't involve all changing magnetic fields. Here, you're moving the loop. So in this case, there's actually electrons in here, and there's forces as you're taking it out. And so this current this induced current may not be due to an induced electric field, but rather due to magnetic forces. Same, anytime the loop is moving, you've got magnetic forces. But a case where the magnet's moving, then you've got actually an induced electric field. Here's another case, the last case, the loop is spinning. So it's there, the wire is moving in a magnetic field. And so you get an electric force. I'm sorry, you get a magnetic force there. So I want to do example 4 now, pulling a coil from a magnetic field. And so here we have a magnetic field. And let's say there is a coil here. And let's say I try to pull the coil out. We're going to find that the induced current, there's like this feedback loop kind of. As I start pulling this, the flux changes. As the flux changes, a current is induced. And as a current is induced, then there's a current in a magnetic field that experiences a force. So this is related to how inductors are used for power steering and that stuff. They can actually apply forces to coils. And you could actually get forces by turning on the magnetic field also. But in this case, as we pull it out, we're going to find out there's a resistance for us pulling it out. And so they have a bunch of values here, 100 loop square coil of wire with side length 5 centimeters and total resistance 100 ohms is positioned perpendicular to a uniform magnetic field B, 0.6 Tesla as shown. It is quickly pulled from the field at a constant speed, moving perpendicular to B, to a region where B drops abruptly to 0. So that's what I should have said. B equals 0. You're pulling it out of the field, so it's not going to be in the field. At T equals 0, the right edge of the coil is at the edge of the field. It takes 0.1 seconds for the whole coil to reach the field-free region. Determine A, the rate of change of flux through one loop of the coil, sure. And B, the total EMF and current produced, how much energy is dissipated in the coil, and what is the average force required. All right, so basically we can outline our plan here. They kind of map it out for you with these steps. First, basically you want to find what's the flux, and then the change in flux, which it's going to lose all its flux. Then from that, we're going to be able to estimate the induced EMF, and then you can estimate the current, and then you can estimate the force on the current. So it's definitely a feedback loop where like pulling it out causes the change in flux, it causes the EMF, which causes the current, and then you have a current in a magnetic field, and then there's a force. And so it's going to feel instantaneous to the person trying to pull this coil out of the wire. All right, so it's some just straight calculations. The total flux is almost the exact same calculation we did before. You have a magnetic field times the area. And, oh, it's a 0.6 Tesla, so much bigger. I used the Earth's field, so that was much, much smaller last time. And then the size of the loop, 5 times 5 is 25, but then that's times 10 to the minus 4, so we have 2.5 times 10 to the minus 3 square meters. And then multiply those together. We have 0.0015 Tesla meters squared. Now we can compute the flux or the EMF. And notice I'm not concerned about that minus sign. We're just going to find the absolute value. We can think about the current using just regular logic. We don't need to rely on that minus sign. That minus sign is not worth our time. But we're just going to take 0.0015 Tesla meters squared divided by the time is 0.1 seconds. And so it's 0.015, and we'll call those volts. So 15 millivolts is what we've got here. For one loop. And so what about, we've got 100 loops. So we're multiplying that by 100. So one loop. So total, we've got N times the EMF for one loop, and that's 100 times 0.015 volts. So we get 1.5 volts. So we got 1.5 volts. Now we can, I think that's A was this first one, and B, we're getting there. What's the current and the EMF over the resistance? So we're dividing by 100 ohms, 0.15, 0.15. So it's back to 0.015, and those are amps. So we have 15 milliamps. So that's B. C, how much energy is dissipated in the coil? Well, then we can do power is I squared R. We know how much current is flowing. So 0.015 amps squared, and then times 100 ohms. That'll give us watts. 0.015 squared times 100. We get 0.0225 watts. Seems pretty small. The total energy is the power times the time, because hopefully you guys know this, a watt is a joule per second. That's how it works. So you multiply the watts times time, and then that tells you how much total energy. So it's pretty small. Multiplying by 0.1, 0.0225 joules per second, multiplied by 0.1 seconds, because that's how long it's going, and we get a 0.00225 joules. So 2 millijoules is what we're looking at. And so what was the average force required? Now we'll think about this. Which way is the current flowing? If you think about Lenz's law, hopefully you guys can get this idea. Current's going to be flowing like that to oppose the change. And so then we've got forces here. If we remember the force on a current carrying wire, ILB sine theta. Well, here theta is 90 degrees everywhere, so we can just forget about that. It's ILB. And so we've got these 3 segments, and the forces in different directions on each segment. And as the book has noted, we don't care about some of them. The one pointing up, the one pointing down, those are going to cancel, because that's the same. But this one side is sticking out. It's not going to have a force on it. So this side is unbalanced, so it has to be balanced by an external. That's the external force. And then this one actually is unbalanced. And so we have to find that out. That's, I think, D. So D, the force, the magnetic force that's unbalanced is the LIB. And so the L is 5 centimeters, 0.05 meters. Then the I is 15 milliamps. And then the magnetic field, 0.6 Tesla. So those are all going to add to newtons, or multiply to newtons. And we get very small, 0.00045 newtons. So less than a millinewton. And I looked in the solution and I found out I was a factor of 100 too small. So why am I a factor of 100 too small? I actually found it. It's not that bad, but I give bonus points if if anyone can figure out, why is this too small? Check that out. All right, so the next topic I want to get at is EMF in a moving conductor. So this section is kind of cool. It's 14.3 because you can completely understand this without any need for induced electric fields. So this is called a motional EMF, and it's kind of a funny thing. So let's say I have a magnetic field, and let's just say it's coming out of the page. So here's some external magnetic field. So we're inside of a solenoid, or we're just on the surface of Earth where there's a magnetic field everywhere. And then I want to imagine a piece of metal just moving through this field. So let's just grab, any piece of metal, solid metal, not a wire loop, and let's just give it some velocity here. So what's going to happen to this thing? Actually, let me make that a little bigger. Oops. Okay, so let's give it a velocity. And so this is just a solid hunk of metal. So what's going to happen here? Well, there's free electrons that are inside this piece of metal, and they are moving. And so free electrons experience a force. But actually, so do the ions. So also, or that's the same for the positive ions. So the positive ions experience a force, the free electrons experience a force, and because of that, the net force is 0. That's pretty good. Otherwise, anytime a piece of metal tried to move through a magnetic field, it'd have a force on it, but it doesn't because it's neutral. Well, I mean, we're going to assume it's neutral. So we have a neutral hunk of metal, so there's no net force on it, but these free electrons can move. And so when they experience a force, unlike the ions, they actually are going to accelerate and ram into stuff. And so which way are they going to go? Hopefully you guys can do that magnetic field rule and imagine you have a negative charge. V cross B is down, but then since it's a negative charge, you have an upwards force on that electron. So on all the electrons. So you're going to end up getting some electrons on the top. They're going to drift up to the top. And guess what? That's going to leave positive ions at the bottom. And so this is just from chapter 20. So it's stuff we're familiar with. But what we've seen happen is just by moving a piece of metal in a magnetic field, it gets a voltage across it. And so then we can give the metal some dimensions here. Let's say it's length L long. We can actually compute a voltage here. So let's see. So I'm going to go into a little more detail about this than your book does. Your book uses the Faraday's law. Actually, I'll follow what they do here just to illustrate that. So Faraday's law works here, even though there's no induced electric field. This is just regular stuff. You can imagine the change in flux here. So as this is moving, you can imagine each little moment of time, so even though Faraday's law works here, it's a little bit, I'm sorry, I'm just going to go through with an actual physical description that your book just keeps avoiding. It's driving me crazy. So what's happening here? I move this piece of metal in this magnetic field. I get a force. I get this charge separation. And so that's going to happen, but this can't continue indefinitely. You know, the free electrons experience force. And so then you get a charge separation. But it can't continue forever. You know, it's not going to build up until every single electron is over on that side. It's going to be balanced. So how is that going to balance? Well, look at what's happening. Negatives don't want to be near negatives. So I've got a bunch of negatives. I got a bunch of positives. I've got like a little capacitor here. I've got an electric field. There's an E that's now been established from this separation of charge. We can think of it as like a little, now it's like a little EMF. That's what they call it, motional EMF. It's like a little battery here. And so what's going to keep that from going forever is that you've got a magnetic force, but now it's balanced by an electric force, Fe. And so your net force on the electrons, if you want to think your net force is your electric force from this newly established electric field that happened because the conductor was moving, plus the magnetic force. And so that's going to equal 0. That's what we call equilibrium. And so what we're saying here is they're equal in magnitude. And so electric force is Q times E, magnetic force is Q times V times B. And so this is a little dangerous of an equation because people just tend to think this is always true, but this is only true because we're getting this nice balance here. It's not that always any electric field is equal to VB, but when an electron is in balance, then that must be true. And so this is the steady state equation. So now we know we've got an electric field, and then we can think the voltage across the piece of metal. Delta V. Here we can think of as the electric field times the length. If you remember that from chapter 17 or 18, I believe, you had the potential was the electric field times the distance. We know the field, therefore we can actually plug this in, and then we get a LVB. And so that is our delta V. And this actually, I'm not going to go through it. You can take a look in the book. They use Faraday's law to derive that. Actually, might as well do it. So we'll take a look at what's called a rail gun. Let's say I have a same situation where I've got my magnetic field. And then I have a bent piece of metal. So this is a little contrived situation, but it might help you see how this could follow Faraday's law. This is a U-shaped wire, just a wire. And now I'm going to take a freely floating bar, like a metal bar, and just sit it here. This is a metal bar. And then let's move that metal bar. So now I'm going to move this metal bar. And so we've already figured out if you have a metal bar that's moving in a magnetic field, you're going to get an EMF. So what we're basically getting is negative charges on one side, positive charges on the other, and we're going to call that a distance L here. You've got an EMF. We figured out LVB, that's the EMF. And then we could think about this is now a circuit because I've got basically like a battery here. You want to think about this as like basically what we've got here is you've got this wire, and then you've got this bar here is basically acting like a battery. So we've got here something like that. So you got a positive end of a battery here. So now you're pumping current. You're pumping current around this way. And so what is the current that you're getting from this? The current is the EMF divided by the resistance. So there's some resistance to the wires. So you've got LVB over the resistance. That's your current. We could also think about this as a rate of change of area. So as this thing is moving, it's increasing the area of loop. And look at which way the current is flowing here. I have the current flowing clockwise, which produces an induced EMF down into the page. And that makes sense with Lenz's law because it wants to oppose the change. As this loop is getting bigger, as this bar moves, loop gets bigger, area gets bigger. And so the induced magnetic field is then opposing the magnetic field that's there. And so finally, I've been avoiding this, but it's a great thing to look at. Using Faraday's law, you can just say, well, it's delta phi, delta T is your flux. And if we think about this bar moving, if this bar moves a distance dx, right? How much area has happened? Well, a little bit of area, we call that, well, I won't call it dx, that's calculus lingo. I should say delta x. Delta x. This area we could call delta area. My change in area of the loop is, well, your delta x is your speed times delta t. So the delta dA is the length of the rod, or at least the width of the loop there, times v delta t. And so if I want to do the flux, change of flux in time, I have b LV delta t over delta t. And so then the delta t's cancel, and I get that same BLV again. So you get the same thing using Faraday's law or this idea of motional EMF. So I like the motional EMF because it puts you can see the nuts and bolts of how it's working with it, balanced magnetic and electric fields. But Faraday's law, anytime there's a changing flux, Faraday's law is applicable. So it covers different causes. And so what's crazy about this is this really is happening for every piece of metal that's moving on Earth, because there is a magnetic field on Earth. And so one example is our airplanes. So your example 21.5, we'll just do that real quick here. It's like I have everything but the actual example. So does an airplane develop a large EMF? And so the answer to this, well, let's just use this example, 21.5, you can look it up, but I'll just copy down the parameters. 1,000 kilometers an hour, that's how fast he's going. Her Earth's magnetic field is 5 times 10 to the minus 5 Tesla, 50 micro Tesla, and is nearly vertical. And so, well, this only works near the poles. Because, well, if your airplane, so the wingspan is really your largest distance, right? So that's where you're going to get a big EMF. And so usually if the airplane is flying in a normal place, the magnetic field, well, when I've been by normal places in our typical temperate latitudes, your magnetic field may, be pointing somewhat perpendicular, but mostly along the airplane. And so you have only this little bit of perpendicular component or velocities like that. So any component of the magnetic field along the plane doesn't count. So at a temperate latitudes, you're not gonna have much. But on the poles, right? If you think of the Earth as like this big magnet, and you've got like the magnetic fields are almost vertical near the poles. So you're flying an airplane near the poles. That's where this is going to be the biggest effect. All right, so let's go back to the problem. Got the speed, the magnetic field. What is the potential difference? 70 meters. So we've got a 70-meter distance there. And so it's, well, let's look at where we got. When we did this, so we're just basically, the airplane is this piece of metal. And so we're just going to use LVB. That's all this whole thing is about, LVB. Equals LVB. So we got to do some converting. 1,000 kilometers per hour is 1,000 times another 1,000 meters, and then an hour is 3,600 seconds. So it's hard for me to divide that in my head. 1 million divided by 3,600. 278 meters per second. And then we're multiplying all those together. So 70 meters, 278 meters per second. And then the magnetic field, 5 times 10 to the minus 5. So it looks like we're going to have a 10 to the minus 2, or maybe a 10 to the minus 1 here. So it's not too small. Times 70 times 5e to the minus 5. So around, well, 1. Oops. 0.97 volts. So approximately 1 volt. So might be more of an issue for satellites. They're going like much, much faster. Another thing that you guys might be interested in, you healthcare professionals, is this example, example 6. Let's take a look here. Electromagnetic blood flow measurement. The rate of blood flow in our body's vessels can be measured using an apparatus shown in the figure, since blood contains charged ions. Suppose that the blood vessel is 2 millimeters in diameter, the magnetic field is 0.08 Tesla, and the measured EMF is 0.1 millivolts. What is the flow velocity V of the blood? Wow. Without giving us a whole lot of the flow velocity. Interesting. So basically, if we can put a vessel between the ends of a magnet, so let's see here, we can get a force. Well, and then I guess we're using this thing. The EMF is LVB. So that's what we're going to apply. We know the L is the size of the blood vessel. The V is measured. And so the unknown is, I'm sorry, the EMF is measured, the V is unknown. So we just basically solve for V, EL over B. That's it. That's the problem. So 0.1, I guess it's 10 to the minus 4. You can just call it 10 to the minus 4 volts divided by a distance of 0.002 meters. And then a magnetic field of 0.08 Tesla. We've already done enough unit analysis. Hopefully you believe that is going to be meters per second. 10 to the minus 4 divided by 0.002 times 0.8, 0.08. 0.625 meters per second. And you could, or also you could 625 millimeters per second. All right. All right, so I want to ask a question again. So we've got these different situations. One case where case one, let's say the loop moves. Loop moves, or somehow the loop is changing shape, and I have a magnetic field here. So let's say this loop is moving here, V like that. So what's happening in this case, we can think about the reasoning for the induced current is caused by magnetic force in a way, because you've got a V and you've got a B. If you want to think about the direction of the force here, B is up like that. Maybe V is coming out of the page there if you want to think perspective drawing, going into the page. Oh, no, I'm sorry. It's just the whole thing is moving down. I was confusing V with the current. So V is actually going down there. And so you can think, what's the direction of force on an electron? That'll give you the direction of the opposite direction of the current. So you get a force if you want to take a look at there. V cross B, you're getting a force coming out. Here you'll get a force going in on a positive charge. The opposite way for a negative charge, but it'll give you the same conventional current. And that's telling us Lenz's law, because Lenz's law then is giving us the current, and then you've got an induced magnetic field inside here that's down, and so that's opposing the change. So this is, we can think as the magnetic field is like actually responsible for this. But here's one of the weird things about electromagnetism is that it actually is kind of sketchy. Like some of this stuff, you'd think it would have the same reason, but this has a different reason. Case two, the magnet moves. And so same exact physical situation. You've got a magnet in a loop. In the first case, the loop was moving. And in this first case, we said, well, there's an induced current, but that's caused by the magnetic force on a moving charge, But what about this other case where there is no moving charge? There's just a V, and then there's still a current. There's the exact same current going around like this, into the page, out of the page. And so now what's causing it now in this case, case two, you'd think it would be the same answer because it's the same physical situation. It's relative motion. Am I sitting on the magnet? Like this case, you could imagine the observer's on the magnet. In this case, you could imagine the observer's on the wire. So which one is true? Well, we got two different explanations. Here, the explanation is a little bit more crazy. Just more new to us, is that the changing magnetic field creates an electric field. And so this is quite a step here, but I just want to mention just one more time, how are these different? It turns out they're not different. If you do a complete version of magnetism and electricity using relativity, you can get rid of the magnetic field. And that's the only way to unify these two features. So there is some jankiness to the level we're teaching this, but it's okay. So I want to focus on this case. The magnet moves. In this case, a change in B creates an electric field. And so what I'm meaning that is, think about a point in space, like a point on the wire. I've got a B, it's right there. It's like coming out like that. And as the magnet gets closer, that B is like getting longer, it's changing, increasing. And so at a given point in space, if the magnetic field is changing, then you create an electric field. So that's the idea. That's really the central feature of Faraday's law, is that you've got an EMF delta phi B delta T. But that EMF is well, I'll go the other way. If we want to think, what's that EMF? It's the electric field times a distance. So we'll say electric field induced. So this is induced from the change in magnetic field. It's induced times the loop length, the distance around loop. And that's equal to the change in magnetic flux. So we're really getting this, it's basically a non-Coulomb electric field that's generated here. That's the only way we can think here, because there's no magnetic force that can happen, because there is no magnetic force for just a magnetic field changing at a point in space that doesn't